Okay, I should be recording now, is my understanding, because I turned my head. I didn't see that it actually officially engaged, but, yep. Okay. I talked about Fatima, the formatting. Your papers are formatted okay. I wouldn't mind if the font size was larger. You use 12 point or something. You're using LaTeX, right? Just directly
I can easily change the font. What would you prefer?
12. It's just because the way I grade. I mean, I'm going to show you right now how I use Typora to export directly from the notebook and how well that works. Her pages, though, she had some other issue, and she was giving me pages that were like 10 inches wide and 20 inches tall, which there's another problem with them, too, that I didn't mention a moment ago, was that rendering everything took a very long time. It was like both of your files are the same size. His renders almost immediately, and yours is like it's going through lots of work to render all the elements out on the page, which as I was getting going with the grading, it was a little bit troubling to me. So what I'm going to do is I will take something other than, well, maybe I can do this one. Yeah, this one's not that long. So I'll just take this one that we were looking at. It does have math in it. Not a lot of math, but it's got some. I'll take this one and just show you how I use Typora. So what I do is if this is the notebook as I like it, I would go over to here and I would say export notebook as Markdown. And it'll create a zip, and I'll just close that because I know where the zip is located. Then I will go into downloads, because that's where it puts it normally. So it's right here, and then what I'm going to do, you have to unpack it. On Windows, you can go look inside of it, but you can't actually work with it because it's still inside the zip. So I'll say extract all, and I'll just let it extract to my downloads folder. And now it's in my downloads folder. Oh, never mind, it already opened up a folder for me. So it opened up the folder, and you can see it's created scalable vector graphics files for all the graphics that were in the Typora. That were in the Jupyter Notebook, and then it's created one Markdown file. So I have Typora running already, so if I just double click on it, it should open up that page. I guess it's opening it up. I think it is. Maybe I'll have to start this over again. There we go. It just opened it up, and it's opened up in the outline mode, which I can minimize if I want to. So here's the complete notebook, and the thing you can do with this if you want to is you can, these were LaTeX commands that I had in here in a raw format, so you can kind of rearrange stuff. Like I could, that was my title, and I might want to put that up over here, and if I do Control/, I get into the raw editing mode, and I know for Markdown a single pound is going to render as heading level 1. And then this one, just delete that one. The other thing it does that I'm sometimes annoyed with, it puts in extra spaces, so you can just go through and delete them, the extra spaces, and it will properly render your math, or at least it should in due time, but there's some things you have to set up in Typora to make it do that. For LaTeX math, the display equations will work fine. I'm not going to go through and remove all these extra spaces that carried over. What it's got available in it, it's got in paragraph mode, though, if you wanted to do display math, you would just do that. Well, I didn't do that in the right spot. If I wanted to do a display math, I could just do a math block, and then it already puts the proper delimiters in, and I could be putting in something like x of t equals a cosine Y, T, and you can see it's rendering it down below. And if you had to do things like stuff that I like to do, this keyboard is very tiny compared to my normal one, so my fingers tend to just, I can't control my actions on the arrow key, so I end up doing worthless things frequently. I'm just going to say, if you want to be able to do a multi-line stack, there's commands in LaTeX that you can add in. And then if I wanted to, I would just say, put that in there. And then I could say, that, and I didn't put the backslash in front of it, so it didn't render it. Then you can get the stack of equations if you're interested in that kind of a setup. So what you have to do to get some of these things set up properly is you have to go into Preferences for Typora, and Appearance is one of them. I use a theme that I've got on the website, and it's been modified so that you can use a markdown command to make a page break, which is kind of nice. So I'll show you where that is. It's dash 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 does that for me. So let me just, but you can get extra themes. You can go out and find more themes on the internet. You can find out open themes or open the themes folder to put a theme in there. Themes are just different formattings you can do style-wise. But my theme happens to be one that was out there that I modified with this extra set of commands in the cascading style sheets or CSS file. None of you do that, right? You don't write HTML pages very often, or if ever, but I learned how to do that a long time ago from my website. So I took that challenge on when I read a tip on how to do that. So let me just verify that it's in this folder. It might not be in this folder, so you might have to go look in lecture notes here. It is not inside of here, so what you'd have to do if you want to get the one that I've modified, you could go into my other class, 5650, and it's a hot link, the same, under lecture notes, and this gets you to the back side, the raw listing of what's in that folder. And down here, I've got this guy right here, Misty Theme Windows 2 zip. So that has a .css file inside of it. If you grab that and then install that for Typora, you'd have that extra command at your disposal if you wanted to go that way. There's now more features in Typora that let you break on headers, but it only lets you break on the top level header, which would be the single pound sign in Markdown. You can do it that way too. Let me just go back over to here. So now I'll go back into where I was. So then under Editor, or maybe, no, it's under Markdown. Under the Markdown section, I like to turn on auto numbering of math equations. I guess you can do a line break at new line, which is a LaTeX command. I haven't tried that. Maybe that works just as well. My solution was an old one. But you also want to turn on syntax support so you can have inline math. And maybe that was what bothered you because you didn't have that turned on, so it wasn't rendering your math that was inline. Maybe. This program changes just, I've been using it for about 6 years now, and it changes every month or two. I mean, it updates. The guy is very responsive. He says he's got to start making us pay for it, but that hasn't happened yet. And then under export, this is some nice features they've added recently. So under PDF export, which is what you're going to do, you can make sure you would set this, say, to US letter. And then you can set up a footer that has pages, a header if you want to. And if you just click on here, you'd see some examples, like number of pages out of total pages. some of the other formatting stuff. I think this Learn More takes you to the author's link. I mean, this is all stuff that was just added in the last few months that I didn't even know about. There was never a way of page numbering, because Markdown is not a language that excels at doing anything but simplified HTML. But if you do write something in Typora, like if you are writing a blog or wanted to write a web page, if you write it in Typora and then export to HTML with a CSS file included, then you put that on a website and it looks beautiful. Everything is built for you automatically, which I guess people that blog, I don't do that. I effectively do that, but I mean, sometimes it's nice, I found. So that would be that, and then you close out of the preferences, and then all you have to do when you want to get it as a document you can turn into me, you just say export PDF, and it's going to give you the opportunity to see, well, to save it. So it's been saved, and now it's over here in this folder, which I guess is still open. Yeah. So now there's an extra file added into that folder that Jupyter downloaded. So this is the demo PDF file, which it's going to pick that PDF viewer, the one in the web browser, but I don't know. It's going off and looking at news of the day. Maybe or maybe not. Yeah. I don't want that, but there it is. And I didn't turn on. Yeah, I did. So the page numbers are at the bottom, just like I requested. And one other thing that I didn't show you that you can do, and I do for some of my materials, is I will, right at the top here, I will go to paragraph and I will insert table of contents, which, why am I not seeing it right now? There it is. So that's kind of nice. And the thing I didn't show you also was that if you want to put in a page break, dash, 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 and then I just move off of that line. You see it's putting in a horizontal rule, and with my theme, that horizontal rule becomes a page break. Any other questions? What I like about it is it has spell checking. The Jupyter Notebook has as a plug-in, but it'll help spell check. You can kind of come back and tweak things, but if you change something in here, like one of these code cells, if you're wondering what that looks like, you just hold down Control /, you'll see it looks like there's the raw Markdown commands, backticks, and then the language it's supposed to render in. So you can also just type in this mode if you want to, and then that just renders it out for viewing. So it's kind of an instantaneous view. It is a two-step process, but I always find something that I need to fix, and I can fix it right here if I want to. And scalable vector graphics are very nice, so they just transfer right from your notebook and they're in here, so it produces nice quality output. Have I used this extensively? Yeah, as a matter of fact, if I was to go over to my CommLab class, when I rewrote the labs with the new Keysight equipment, I did everything in Typora. I did a combination of just authoring in Typora, and then I merged in stuff from Jupyter Lab notebooks. I brought in a lot of exterior graphics. That's what you see here. So I just put in graphics. I created nice tables in Markdown, and you can do a lot of stuff in here. I think it's almost like I don't need to use LaTeX as much anymore because this is more of a rapid environment. It's not as customizable, but it's pretty rapid environment, and it works well with Jupyter, so. But all of the course notes are written in LaTeX, just like you're using. That's what I have on my system. And I happen to use, I used to use, let's see, I've used different LaTeX editors over the years, depending upon what operating system, but now what I like to use is the one that's in VS Code, because that one is just kind of included for free.
Yeah.
I have it right, I think I have it in here, maybe I don't. I have it on my other machines though, but you can just type LaTeX. So I use this one, LaTeX Workshop. That's what I happen to use right now. Have you used it before?
I just am so comfortable with Vim that I use Vim for everything.
Okay.
Like my workflow is just like 5 terminals. For Python, I don't use Notebook. I don't.
Yeah.
Maybe it's nicer, but.
So here's what I like about the notebook that you maybe haven't realized yet. When you write stuff in a notebook, you have your code and then you have your comments right there, so that if you are done with that notebook, it's self-documenting. I mean, if you write notes to yourself, so you can go back to it later or share it with somebody. For me, I'd like to have some reminders about what did I do when I come back to something after having not touched it for a long time. And that's regardless of whether or not I'm writing in Python or whether I was using it in my C++ workflow during my sabbatical. I just created files. I created header files in the notebook. And then I had a record of what was I creating. I imported and exported binary files that were my interfaces to the C++ stuff that I was doing. I'm actually setting up to do that right now in the DSP class, so that's why I've got some stuff set up in here right now. Just a little example, and you can actually do a Jupyter notebook if you want to right inside, because they have the plugins for that too. Or it's called an extension.
Yeah, I'd like a makefile that runs all of my Python scripts, because they'll automatically save SVGs, and then there's a make dependency to run PDF LaTeX
Okay.
after all my scripts run.
Okay. Well, see, you've focused on the streamlined workflow. I
I have a
mean,
very command line.
yeah, no, I like command line too. I mean, so I have my terminal down here, and for what I'm going to have them do, they are going to be using the makefile, and my makefile is just a simple one set up for C++ building and that sort of stuff.
Makefile.
What's that?
I said it looks like a makefile.
Yeah. Where I work, though, they use CMake a lot, and I haven't really learned that very well. The makefile idea I just like because it's simpler.
Yeah.
But that's not the core of the team. The core of the team is CMake and those scripts or whatever, lists, I guess they call them, right?
I've used that once. I've also used Ninja,
Okay.
which is another build system.
Make is the original one though, right? Because CMake creates a make, I believe, at the
Yeah,
end
it's
of the
like just
day.
a high-level language that turns into a makefile.
Yeah. So I'll stick with the makefile for right, I mean, that's just the way I've been recently.
Yeah, I agree.
And if I need to add command line options, like include a library, I can just tweak my makefile to have a library import, or if I need to turn on or off optimization, I can just go -O, whatever, right? We don't need to do that in Python though, or at least I don't. Okay, so let's get back over to this and
But yeah, so if you want, I can export bigger fonts for.
yeah. I'll make it through the grading. I didn't get through yours because I got bogged down. I was looking at all of them, and Robert.
Do you want me to just resend you homework 1 or just in the future?
I'm about ready, yeah, in the future.
Okay.
I can manage it. What I do is on my iPad, which has got the 12-inch screen, I split the screen, so on one side of the screen I have my answer key where I annotated it with the point values, and then I bring yours up
Right.
in the right-hand screen, and then I scroll it, and then I'm using PDF. I use Acrobat for iOS, and then I just scroll on top of that.
Yeah, so I can see 10 being small.
Yeah.
And a dual screen iPad,
Yeah.
that's too small.
Yeah, well, I did that because I bought the big iPad and I was able to do that. That was during the start of COVID when I said, oh, I bought this iPad. Why did I buy it in January before COVID started? And then I said, oh, I guess I bought this for a reason that I didn't understand until later. So, I mean, my wife thought I was crazy having such a big one. But I play music and I can set it on a stand and I can put music, have music brought up. And there's actually a lot of tools for the iPad, like changing pages with a foot pedal, or, there's just all kinds of apps out there that you can go with. Okay, so I also, I want to make sure I will do this. This is the new version of this tool that I use for lecturing off of. What's it called again? Drawboard. And it seems to be very unstable. I let it go on my system last week and it seems to crash a fair amount. So I want to just do this. It now has a different interface, but it's a much different interface that I'm going to have to get used to. I think we all don't like software that you like the feature and then they come out with a new version and then they get rid of something and put something new, and it's like, why did you get rid of that? I like that. But it's progress as far as they're concerned. I want to make sure I'll be talking about some of the hints that I posted in the hints page, which is now on the website. So finally, hopefully that Typora overview was helpful for all three of you. We were getting into statistical averages. This is related to one of the homework problems where you're generating ensembles. And this was the first go at a randomly phased sinusoid. And then I'm going to revisit this basic example about 3 more times just to do different things with the randomly phased sinusoid. So for starters, we have statistical averages, so that when we have the ensemble, remember that's slicing down through the ensemble, if this will work for me. Looks like it's not wanting to work. Looks like it's not wanting to work right now, but go back to this way. So we're slicing down through the ensemble, and then that's a random variable that's characterized by the ensemble. Remember, all the sample functions, and then you slice down at a particular time t, you can get all the different statistical measurements. So here's the mean. So this would be the ensemble mean. Frequently, you end up wanting to use the fundamental theorem of expectation, so you can just drop that inside if you want to. So here, I wish I could draw right now. I have to understand why this has a way of quitting. It's been a long weekend, so it got tired and it decided it can't work anymore. Okay, take the battery out, put it back in again. Does that sound familiar? Okay. So I just wanted to say that that is some function g of x, like we talked about earlier for the fundamental theorem of expectation. T is just a parameter, so don't just ignore it. It's just a parameter in the expectation operator. So now we'd go in and find that statistical mean as a function of some x, as a function of x, and then we have to weight it by the PDF on x, which is also got a parameter in it, t, for the time being. Covariance could be calculated the same way. It's now you're going to be sampling with two different random variables, one at times t and one at times t plus tau. And then one that we spend a lot of time with is going to be the autocorrelation function. That's where you're now going to sample at two different times. So if I was to go back up here to this picture, T1 and T2 are the two sampling instants. So we have a joint PDF associated with those sample times, and formally then this is what that expectation looks like. It's a double integral because we have a joint PDF. But that's only written as a double integral because we're looking at it as a PDF on X. What we're going to do is pull a standard trick in this example with a randomly phased sinusoid where you're going to see that double integral go away, and it's just because of the way we're using the fundamental theorem of expectation. That's the whole key to success. So we're going to replace x by some function of the underlying random variable, which in this case, for the randomly phased sinusoid, it is phi. So that is the random variable of interest. So we write a function of phi that we can use as the substitution in the calculation for the statistical mean. So now we just need the density on phi, and that only shows up in the argument of the cosine. So we have a one-dimensional integration. And in this case, because phi ranges from minus pi to plus pi, or from 0 to 2 pi, we're integrating over one full cycle of the cosine as phi ranges from 0 to 2 pi. This is a very important aspect because in the homework problem where you're doing the simulations with the ensembles, you first do it with random phases chosen uniform on the interval 0 to 2 pi, and then you do it on a narrower interval, one that's no longer one full cycle. And then that is going to avoid getting 0. You're going to get something else, and you will see that in your experiments. Okay? Now, is that practical? I mean, this is the practical random epoch scenario that when a cosine wave impinges upon you, it will have this distribution. I mean, it makes sense physically to say it's distributed equally likely between 0 and 2 pi. It would not be fair to say that the sinusoid as it impinges on you is just varying over 0 to pi over 4 or something like that. It's not as typical. It's certainly possible, though, in a certain environment. But so that's one of the things that problem drives you on. To do the variance, do the same thing. And when you do this, for the case of the variance, the mean is 0, so you don't have to change anything in this calculation. You just have to square a cosine 2 pi f naught phi, and then use the double angle formula, so you get 1 plus a term that has 2 phi in it. And again, now when you integrate the second term there, the cosine of 2 phi, you're integrating over 2 cycles, so that goes to 0, and you're left with just a squared over 2. And the reason why I said familiar is a cosine wave of amplitude A in a 1 ohm system, you would say the power of that cosine wave is a squared over 2, right? And if you're working in a 50 ohm environment, you can remodel it. V squared over R would be the power, so you would just be dividing by 50 to get it in watts, or convert it to milliwatts or whatever. Okay, the autocorrelation is more complicated because now we have two different time samples. We have t plus tau and tau, and you could think of this as T1 and T2, or T2 and T1, whatever, but I'm doing that here because I know that something's going to happen, namely the dependency on T is going to go away. So I go through and take the product, get two terms. Again, the second term has the double angle in it. As a student, it's D. So that integrates to 0, and you're just left with a squared over 2 cosine 2 pi f naught tau. So that is the autocorrelation function for a randomly phased cosine, randomly phased on 0 and 2 pi or some 2 pi interval. And you can also observe that if you just set tau equal to 0 or t1 equal to t2, then you get the variance, as long as the process has 0 mean, but in general it would be, as I've got shown there, minus the squared mean. So this brings up an important result, namely that for the randomly phased sinusoid on 0 and 2 pi, the dependency is only on the time difference. So it's only on the time difference between the two sampling instants. So if I was to scroll back up to here, and if I would try to get this silly pen to work again. That's tau, and that's what we're going to be considering most all the time as we move forward. That is processes that are at least wide sense stationary, meaning that, the definition comes up here momentarily, that it's only, the autocorrelation is only going to depend upon the difference between the two time slices. So it can move down the timeline backwards or forwards. It's the difference between where the slices are taken that is controlling it. The tau value, which is also called the lag value. It's called the lag value because when you're looking at this idea of sampling, you're lagging one sample through the ensemble from the other by tau. Okay, so that makes us start thinking about stationarity. What does it mean to have a process that's stationary? So strict sense stationary means that the first order PDF is independent of time, so that the mean is always a constant and the variance is always a constant. And then in terms of the autocorrelation function, the joint PDF is just a function of the time differences, so that makes that happen. And then strict sense also gives you nice properties for higher order moments where you're sampling, say, more than 2 time slices, but we're generally not looking at that. So a less strict assumption is to say wide sense stationary, which is WSS, if the following are satisfied. So this is just a statement of what ensures a process is wide sense stationary if its mean is a constant and its autocorrelation depends only on the time difference, not on the time origin. Now, wide sense stationary is going to be the norm, but does that mean a typical process is always wide sense stationary? No, but if you're sending a process through, say, a filter or something like that, there will be a transient that has to wipe off the system, and we'll be looking at systems a little bit later too. But if we consider after it's gotten into steady state, after the time constants have run their course in the system, like a filter, then the process now looks wide sense stationary. A good example of that, for me at least, this is the backdrop for essentially all my home pages. So this is an ensemble of noise going through a low-pass filter. And behind the graphic right here, you'd see that all of the processes were starting from the origin at 0 because the systems came up from 0 initial conditions. But then They each follow a different trajectory because the noises, sample functions are different. But then as it rolls along and is in steady state, now I would say way out there, like at the right side of the graphic, that would be a Whitesense stationary process because the transients are gone. And that's the nature of how I generated it. There's no time varying statistic. But in mobile radio communications, not true at all because things can change, right, over time. Fading is a function of time. There can be some other local disturbances that are going to be changing with time. But still, even in mobile communications, on a small enough interval, things can appear Whitesense stationary. On the wider scale, then they're not stationary anymore. So different things are done over the years with different types of schemes. Like in the original GSM system, they were interested in characterizing the channel and the delay spread in the channel. So they would put that mid-amble in. I think I talked about this the first day or so, where you'd receive a frame of GSM, Global System for Mobile Communications, and it happened to have been in the beginning GMSK, which we'll talk about here eventually. But so that frame of data would have a mid-amble inside of it that is known at the receiver, and it would train off of that known mid-amble to determine what's going on with the channel. And the reason why it was chosen in the mid is because if things were going to change over that whole frame, then putting the sampling of the known data bit stream right in the middle means it's going to be helpful both at the beginning and at the end. Whereas if you put it only at the beginning, then by the time you get to the end, things might have changed somewhat. So that was designed to be a mid-amble, as they call it, known sequence for training and making adjustments to equalizers. Okay, cyclostationary is a different definition of stationarity. It says Whitesense cyclostationary if the mean and autocorrelation function are periodic in t. So that just says the mean can now vary with time t, but it has a period t naught, and the autocorrelation function has that same property. It will repeat every t naught seconds. So then when you're going after the difference, you get the scenario shown here, Rxx of t plus tau, comma t. I'm bringing up cyclostationarity because it's something that people talk about in digital communications waveforms. There's always a clock, and then there's a periodicity of the carrier, but periodicity of the clock makes things cyclostationary, and in certain types of signal processing operations, that cyclostationarity behavior is exploited for feature extraction, trying to extract some features about a waveform that may help, like in cognitive radio, there's techniques involving cyclostationarity properties for extracting is the primary user, the PU on, because the secondary users, the SUs, want to know if they can do something. So they might use a feature extractor, cyclostationarity based type that has good performance in lower signal to noise ratios. So you
Does
hear
that have to do with the relative frequencies of your carrier and your clock? Or
to be able to exploit cyclostationarity.
yes.
The carrier frequency I don't think matters, but the clock, if it's, trying to remember how this works out because I haven't studied it for a while, but I had a student that was using it. Well, students that have done cognitive radio theses have generally reviewed these types of feature extraction means. They're more complicated, though, than other types. Another application of cyclostationary is in feature extraction of an unknown signal. That periodicity can be used to exploit, like the chip rate for a spread spectrum signal. I had a my first PhD student. We did a lot of that under a contract. So it's just the fact that a waveform has some periodicities in it means that you can exploit it, and cyclostationarity is what kind of reveals that or makes that revealable. I'm going to show you, we're going to look at a random sequence bit stream here in a little bit, and when I look at the simulation, I can very easily reveal properties with a simple operation, which is related to the cyclostationarity business. Okay. So let's just take another example, a product. This would be a signal, a wide sense stationary process X and a sinusoid. So this would be a good comms application where X of t would be like the data waveform, baseband data modulation, and cosine is the carrier. There's no random phase shift this time around in this example. So we go ahead and calculate the mean, and we get the mean from the cyclostationary, or from the wide sense stationary part, X of t, but the X, or cosine 2 pi f naught t, just appears as a time varying constant. So it just comes right on through. So we're not stationary. We are cyclostationary though. Autocorrelation, go through that. We get a function of tau in one term, but then this term is time varying. So again, it's not wide sense stationary because it has that time varying term in it, but both of them are wide sense cyclostationary. We're going to come back and look at that again after we make some additional assumptions. I just wanted to point that out. Mostly I want to point out the fact that you can make a process that was wide sense stationary time varying very easily, and then it kind of destroys some of the nice things we're going to be looking at. But then with additional assumptions, like random epoch, it becomes stationary again. Okay, the next little topic here is ergodicity, which is a set of definitions. A process is ergodic in time if time and ensemble averages can be interchanged or interchangeable. So remember, ensemble averages is averaging vertically in the ensemble. Time averaging is just taking one sample function and doing the time average. And that's what instrumentation would do, whereas theoretical simulation analysis would do the ensemble part. So there's a lot that people have written about ergodic theory. When I was first teaching my random processes class a long time ago, this book right here, 1986, it seems really old to you guys. I was only a couple years into teaching here. I started in 1984. That book was written by some engineering professors somewhere in California. I forget which school it is. Maybe it's UC Berkeley or something. They were almost like pure mathematicians. So they went into a lot of detail, and they wanted to try to explain the finer points of ergodic theory. I don't pull that book out anymore, but it was at a time in my life when I was influenced by the mathematicians that were trying to make sure I wasn't cheating on something, because I had been to conferences where these type of people would speak, and they were always harping on electrical engineers that were hacking the math too badly. So I tried to gain some respect for the whole idea that don't hack the math so badly that you created something that's simply not true. So I got more interested in it, but still, for the teaching of this class, we really don't have the time to hover on that too much. But the idea of the ergodic theory would be, if we define the ensemble average like we've been doing, this is a function of the random process X. We use fundamental theorem of expectation like we have been doing, and then the time average is just the angle brackets at either side. That's what Ziemer and Tranner book uses for the time average. And that little I that I put on here is tracking which sample function it happens to be. And you just happen to get the ith sample function, and then you average over all time. You're doing both of these things in that simulation problem, so you get a chance to try these ideas out, except a sum is used rather than an integral because it's a discrete time process, but it's still the same idea. You're going to average over all the samples. So that if you have an ergodic property, namely whatever in terminology of the function g, then you say the process is ergodic in that sense. So time average is in general a random variable, but tends to be a constant for a particular case of an ergodic process. So both of those will be equal to each other. And here G is just generic, depending upon what you're doing. If you're doing mean ergodic, then it's this property that you're interested in, just the mean, the vertical statistical mean, and the horizontal of any sample function. And this is what you're playing with in the simulation. You get to try, like I said, try it out. And you'll see that it just leads you down the path to discover, is it true or is it not true? And you just do experiments. It's like I've got this whole ensemble that you created in the matrix, and you can test it out. Autocorrelation ergodic, we'd like that to be true, and that's would be saying that the ensemble autocorrelation is the same as the time average autocorrelation, and this is the time averaged autocorrelation right there, where you're just going to place what's inside the angle brackets there inside this time average operator. So let's go back and visit the randomly phased sinusoid part 3. So we have a randomly phased sinusoid with some distribution for phi. We're assuming, once again, whenever the book or I say randomly phased, that means uniform on one full cycle. Simulation problem, one part does it that way, the other part lets the uniform be less than a full cycle. Just trying to drive home that it hinges on that. I mean, I like that problem because it teaches you to be careful. So compute the time averaged mean, average one period, or average a cosine wave. No matter what phi is, that's going to be 0. Do the time averaged autocorrelation. We can take the time average operator and break it apart using linearity, because the time average operator is a linear operator, and then have two terms come out of there with the a squared over 2 out in front. And then because we're averaging with respect to phi, well, we're considering, not because we're averaging with respect to phi, but because we have this 2t in there, we know for certain that we're going to be averaging over all the possible cycles. If we just did this even over one period, we'd average to 0. So this averages to 0. So we get a consistent result from the original ensemble autocorrelation, a squared over 2 cosine 2 pi f naught tau. I don't know if that makes you feel good. You're supposed to be able to say, hey, these simple waveforms, I can see that time averages and ensemble averages interchange. As Keysight relies on this for their instruments. Certainly we talk about a theoretical autocorrelation function and then power spectrum. How is it that the instrument can get a power spectral density that looks like the ensemble power spectrum?
Would an intuitive understanding be essentially, maybe this is wrong, but a randomly phased sinusoid always has a mean of 0, and then if your phase is random, then looking down a slice, you should always get a mean of 0, right?
Yeah.
Is that a good intuitive way to appreciate that?
Yeah. This you gave me a segue for what I wrote down here. This is kind of doing that. It's saying it's the DC component is really what it is, but if there's no bias on the waveform, then it's 0. If it's centered around 0 in the amplitude scale.
Right.
And squaring it will be the DC power, and then subtracting, well, the mean squared power is the total power, and then the variance is the AC power. These are really important things from an instrumentation point of view. The last two generally are the same, especially if you're measuring instrument like a Keysight spectrum analyzer has a blocking capacitor and doesn't respond to DC. It will just give you the total AC power. But if it's a FFT-based spectrum analyzer with coupling that's DC, then it's going to be different. But these are important things when you're in the lab, though, and I always emphasize this when I'm doing the comm lab or when I'm thinking about taking measurements in the lab versus the statistical side. Okay, next we're going to look at multiple random processes, and it's just going to be 2, but it could be generalized. So cross-correlation, we got cross-covariance. Pardon me?
Can you scroll up for 1 second?
Yeah.
I just wanted to take a really quick look at that.
Okay. You know you can download the notes too if you want to.
Yeah.
Everybody does it differently. Nobody here is writing on a tablet or anything, but some people print the notes and then they take notes on the notes. It's your choice if you want to print the notes out.
I'm good.
Okay. Especially since I unlocked them for the world this year, I decided to make a break and just say, okay, I won't work here much longer. I'll just release them and I'll duck, and hopefully nobody will complain that I've got somebody's copyright violated somehow or another.
Isn't there some free use?
There is, but you have to be careful with that. I'm not worried myself. My son does productions at our church for streaming services, and somebody used a media clip that was a few too many seconds long, and he's in charge of streaming it out to YouTube and to Facebook. And YouTube didn't have a complaint, but Facebook immediately with their AI or machine learning algorithm sensed that this was a copyrighted video and the clip was too many seconds long. It got blocked. It got pulled off automatically. So he had to go back in later and re-edit the whole stream and clip that section of it down so that it met the seconds limit, and then re-pushed it, and it was accepted. I don't post videos, but I guess that's there for our protection, right? So we don't violate copyright laws or other things are sensed. Okay, cross-correlation, we have 2 processes, and we want to take the expected value of x at t1 times x at t2. If we have an uncorrelated process, then the definition of uncorrelated says this right here. It says the expected value of the product is the product of the expected values. And this follows from the definition of uncorrelated random variables. If x and y happen to be jointly wide-sense stationary, then we would get our xy of tau. And this would be the cross correlation for a measurement system where you're probably going to do it using a time average. In other words, you can get at this cross correlation in a time average sense. And this is useful in synchronization. Say in the spread spectrum system, you have the local spreading code that you're using, and you have the received signal that has that local, or has the spreading code embedded on it. You have to figure out where the alignment of the 2 waveforms is, like in GPS is one application, and this cross correlation would be taking the received signal and the locally generated reference, cross-correlating them and looking for the correlation peak, and then using that for despreading purposes.
I guess to do that, you need a decent amount of memory, right? To get remember enough of the received signal that you can calculate a decent correlation.
Yeah, and that's a function of, what the signal-to-noise ratio is too. Spread spectrum signal, though, you can pull the correlation peak out of noise even with not a super long length. I mean, that's one of the whole keys of spread spectrum is you can pull things out, and if there happens to be a superposition of other signals that have different spreading codes, their cross correlations are zero or small, so you can still pull it out. That was the basis of code division multiple access, which we'll be studying that eventually. It's not a popular system in the commercial sector right now, but it's still military applications and still out there. Okay, sum of random processes. If you go ahead.
I guess the thought is if the noise is white, then once you take a long enough interval, it won't affect your autocorrelation, right?
Yeah, it doesn't necessarily have to be white. We're going to be talking about that pretty soon though, like very soon. We're going to look at spectrum analysis, power spectra starting right here. So let's just look at another scenario. This is a very common scenario. We looked at the product of two signals before, now we're looking at the sum. This is very common, where we have signal plus noise. So Z of t is x plus y, assuming that they're jointly wide sense stationary, then we can go through and expand this out. So this is the starting point, and this is, so you start here, and then you use linearity of the expectation operator. What I mean is that superposition holds when you're taking the expected value of some combination of signals. So here we want to get the autocorrelation function on that superposition. So we go in and drop a replacement in for z of t plus tau and z of t. And then in the next line there you see I've already done that. So now you start blowing it apart into its subsequent terms, and you get 4 terms out of this when you do that. And then you can individually characterize using the wide sense stationary assumption to say that we have all 4 of these pieces. So these are perhaps the dominant ones. Autocorrelation on X, autocorrelation on Y, and then you have these cross-correlation terms, which if the waveform is uncorrelated, X and Y are uncorrelated, then those terms will break down into the product of their means, and if one or both are zero mean, which noise is typically zero mean, then it makes those cross terms go away. And then we also get the definition of an orthogonal process. So under the uncorrelated assumption, we get this immediately, assuming one is at least of zero mean. So it's the sum of the autocorrelations. So I'll go into power spectrum. Very valuable concept because we need to have the frequency domain in digital comm to just see what's going on, because we worry about adjacent channel interference, co-channel interference, all the things that happen when people are tightly nested in the frequency domain trying to do as much, gain as much capacity out of a given piece of spectrum as possible. So the way it's defined typically is starting with a sample function, we form a truncated sample that runs from minus t over 2 to plus t over 2. So it's like and then there'll be other sample functions in the ensemble, and that's what the I is indexing. So we define this x capital T, which is just on the interval minus t over 2 to plus t over 2. That's a truncated sample function. And then we form the energy spectral density of this, and this goes back to COM Systems 1, where the energy spectral density is defined as the magnitude squared of the Fourier transform of a waveform. I haven't done anything with randomness because right now I is just the index into the sample function. So we're just saying the energy spectral density of a particular sample function that's been truncated is this, which is written as the magnitude squared then of the Fourier transform of that truncated sample function. The power spectral density of a particular sample function is that value divided by t, and it's really good at this point to see is that making sense. At least I like to do that, because if I'm in the lab taking a measurement, I want to know, is this really going to be the proper units? So do you want to check that just to make sure? What is the units of power spectral density? It's got to be power in watts, right? And if it's a density and it's in the frequency domain, it's got to be the units of per hertz, right? Is that just, that follows naturally, right? So is that what we have here? So we have, let's assume that the waveform is a voltage waveform. So in little x, we have volts as the unit. We're going to take the magnitude squared, so we're going to get volts squared. And then once we take the Fourier transform of that, we're going to be including a dt in the Fourier transform integral, right? So that will put a units of time up top, and if you flip that to the denominator, it would be hertz in the denominator, right? T on top, 1 over t is frequency. I'm not trying to be super rigorous, I'm just trying to, I frequently do things like this, and I think everybody should do that. If you're questioning your units, just make sure you're on the same page as you think you are. So we have v squared per hertz, and if this is going to be 1 ohm system, then v squared over 1 ohm is what we're talking about. So that's going to be watts. Except I just messed something up. We're going to divide this by t, and it's going to be watts per hertz. So what I screwed up was let's see, how did I screw this up? I have the magnitude squared, but it's integrated over capital T seconds. So I think that's still right. Now I want to just fell into a trap. Let's see, v squared, integrate for t seconds.
Or doesn't it look like it would be watts per hertz squared? I mean, that's wrong. That's what it looks like.
No, you're right. No, you're right. Because
Oh, because you divide by T in the power spectral density.
yeah, the units inside of here are volts.
Or volt second.
Yeah, volt second or volt per hertz. But then when we take it outside, now it's going to be v squared over hertz squared, just like you said. And then when we divide it by t, we'll get just v squared over hertz, because dividing by t is the same as multiplying by hertz. So, yeah, thank you. See how easy it is to mess things up like that? And then you're going to be going to your manager saying, this doesn't work out right, and he'll be saying, "What, you made a dumb mistake." You don't want to do that if you can help it. So watts per hertz. So the ensemble average is going to be, to get the power spectral density then, is to let t go to infinity, so the observation interval goes to infinity, but that is after you've taken the expected value. So you're taking the expected value, which is averaging over the ensemble of all of the sample functions in cap t seconds, and then you take that limit on the outside. And this is formally the definition. However, that doesn't look like to be a really practical way of calculating the power spectral density. It might make sense in a measurement setting, but it doesn't make sense. Well, in a measurement setting, this makes more sense, but you only have one sample function in the ensemble. But in terms of a theoretical calculation, you don't have an easy means of obtaining the power spectrum. So then we rely on a theorem called the Wiener-Khinchin theorem, which links the power spectrum and autocorrelation function together. And this theorem just says that for any finite tau, in interval u, the integrate over of length magnitude of tau, if that integral is bounded, then the power spectrum is given by the Fourier transform of the time-averaged autocorrelation function. That is useful unto itself, but there's a corollary that says for a wide-sense stationary random process, such that the magnitude of tau times Rxx of tau is bounded, then we have this key result right here, which is what we're going to be using. That is equal to the Fourier transform of the autocorrelation function. So when you get down to it, what this is saying right here is that the autocorrelation function has some shape that decays versus tau rapidly enough so that when you take tau times it and look at the magnitude, it's still finite. Does that make sense? As tau gets big, the autocorrelation function is naturally decaying, like with an exponential. In the linear term in the numerator, tau is still doesn't dominate. The exponential decay dominates, so it doesn't go unbounded. It stays either a constant or is something that is certainly less than infinity, and then this result holds. So this is the standard that we live by pretty much in this class, that we can do this. So if we apply this definition now to the randomly phased sinusoid, where we have the autocorrelation function as a squared over 2 cosine 2 pi f naught t, take the Fourier transform of that, and we get the two delta functions, one that's has a spike right here and another spike right here. This pen is really driving me crazy. I keep having to click it, but so we've got two delta functions, and another related thing is that the power spectral density when integrated should give you the total power. So the total power here is Rxx at 0. Remember, that was sigma x squared, which is the total AC power. If you integrate this power spectrum, you get an a squared over 4 for each delta function, and they'll sum together to give you a squared over 2. So that also is a comforting thing. If it's the cyclostationary type waveform in the wide sense, then a corollary says that the power spectrum is the Fourier transform of the time average of a cyclostationary process, and this ends up being equivalent. It gives you the same type of result. So if we had a wide sense stationary random process or a wide sense station, or cyclostationary in the wide sense random process, and then we form the time average of it, we can take that, we can Fourier transform that and also get the power spectral density. So some people prefer to think of digital comm waveforms in this sense without having to make any random epoch assumptions. So we can return back to the modulated carrier process we looked at before, and then we know that this is a cyclostationary process because it's periodic in F naught, or the cosine makes it cyclostationary, and then we can do this time average technique, and then we will get the same power spectrum out of this thing. Where this is locating the spectrum of the baseband modulation. So see if I can draw that. So if you started off with that's the spectrum of the baseband part, and then when you modulate it, it shifts it up, and you also get the 1/4 factor in there too, which I didn't show in this picture, but this is useful for carrier-based modulation. So a nice set of properties for wide sense stationary random processes, their autocorrelation function is that Rx at 0, which remember is the AC power, that is greater than or equal to the autocorrelation function for any other value of tau. And this is a nice sensible result. It just says that if I'm correlating two waveforms, and I'm going to use my thumb as the example of how the one waveform is sliding past itself. When they're perfectly aligned and I'm finding the expected value of that product, that's going to be Rx at 0, which is the total power. If I change the alignment, I don't get as much correlation, and I'm never going to see it exceed what it is when it's perfectly aligned, which I think makes sense intuitively. It can't get bigger if you slide one side or the other. And the proof of that comes about by just setting up this inequality. I don't know if I'm going to really go through it. I'm just going to say this is the way you can prove it, though, is just write this out, expand it, take the expected value of both sides, and then you can establish the inequality. Ultimately, you're going to get down to here, which is the statement that was made at the beginning. Second property is the autocorrelation function is even in tau. And so you can go to a positive lag or negative lag, and you have symmetrical results. And if you go to take the limit as tau goes to infinity, you will settle onto the DC power in the waveform. So try to go back to this. If it has a non-zero DC power as you lag further either side of 0, it will just settle down on the DC power. And if you have a periodic autocorrelation function, then you can establish that at one period away from 0 lag, the process repeats, so then you just have that periodicity property. It's similar to a cyclostationary process. Final property is power spectral density is non-negative. It can it always has to be greater than or equal to 0. And it follows from the original definition of the power spectral density in terms of this expected value of the magnitude of x of t. There's nothing inside there that's less than 0, so it has to be positive. And a simple proof also that I like is if you have a signal that has a power spectral density that were to be negative, and then you were to send it through a bandpass filter or a filter to only filter out the section where the power spectrum was negative, then you would have that signal that comes out of the filter would be sucking power. I mean, it's negative power spectral density, which makes no sense. A waveform delivers power. It doesn't pull power out of something. So I tend to like that idea better. But we haven't talked about filters yet. And then one other thing before we go on to this really important example that I didn't, for some reason or other, I don't know why I don't have that in here, but what about complex random processes? We haven't talked about that really at all. And so when you have a complex random process, I think actually this comes up later in the notes, but I'm just going to try to write that in for right now. So when a process is complex, then the typical definition would be something like it's the expected value of the first times the conjugate of the second. And if you're just looking at how to prove this symmetry property, number 2, for the case of complex, that's what the property is going to be, and to see how that comes into being is right here. Put the conjugate on the second term, and then if I rewrite it by putting the non-time shifted signal on the first term, then I'm going to take the expected value in the normal setting, except I have the conjugate there. So what you would do is you would say that I can make this, I can carry this out, but I'm going to have the conjugate, an extra conjugate when I'm left over. And another part of this property in the terminology of expectations is it's first minus the second. So it's always, when you're computing for a wide-sense stationary process, what is the autocorrelation function? You put the two components inside the expectation operator, and the convention, you can use the other convention, but the convention the book uses is always say it's the first time minus the second time. So when you're computing things, it would be t plus tau minus the second time, which is t, which is tau. So if I change the orders up, which is what was done right here, this would be t minus tau, which is equal to, no, t plus tau, I mean, which would be minus tau. So that's how you can make this proof work out. You have the minus tau in there, so this is and then we have to throw the conjugate on there, because if we flip it back to the other side, that conjugate has to be dropped onto there because of the orientation that we've used in order to prove that Rx minus tau is equal to R conjugate of tau. I know it doesn't look quite right, but I haven't really fully organized it at all. We'll get back into this, I think, later when we need it. I think the book did not include complex waveforms right now because it's just going to add confusion. So before we take the break, I want to do this important result because it's something that is very tangible, and then it's also related to something you're doing in the homework. Power spectra of a data waveform. So this is a classical random pulse train. So the random pulse train incorporates the bits or symbols. Those can be plus and minus one amplitude symbols. They could be a whole they could be a mapping like plus minus one, plus minus three, plus minus five, and so on that we'll see later for an M-ary type of random pulse train. And then P is a pulse shape. T is the symbol or bit period, depending upon what type of modulation it might be. And then finally, the delta is a uniform random variable to establish a random epoch for the arrival of the pulse train edges. And if you think that's not nice, you don't like putting that in there, then you can omit it, and then you have a cyclostationary process, and then you can go about working from the idea of a Whiteson stationary cyclostationary process and get the same result. I'm pointing that out to you because I've been indoctrinated from both points of view. I like the simplicity of just putting in the random epoch, the delta, but when I did work with this PhD student a long time ago, we went to the conferences. There was somebody from UC Davis, who's now a retired professor. He said, that's not right. You have to treat it as a cyclostationary process. So there's two schools of thought on this. I think our textbook, though, simplifies things by justifying the use of the delta to make it have a random epoch. And then that ends up working out a little bit cleaner. So how do we get the power spectral density? We have to go after this expected value right here, the product of the two random pulse trains, one that's shifted by m and the other that's shifted just by k plus m and k, because we've got to translate this idea through the modeling. So you can't assume that an is multiplied times an, because if the time shift is great enough in the waveform, you're going to be on a different bit or symbol in the pattern. So you have to incorporate that. And so what I've done is taken the double sum that we would naturally get out of this and just drop it in there and then make a variable change. So the variable change is to work with k and m, and then n goes away. And the substitution was this to get rid of the n in the double sum. Now we've got expectation of that double sum, and if you go down to the next page, we can assume or make the assumption that the random epoch time, delta, and the symbols or bits, a sub k, are independent. So when we're looking at the expected value of this product in here, we've got two different random variables there at different index values, and then we've got in this other part of the expression, we've got a function of the random variable delta. So we've got four different things multiplied together. It's quite messy if we assume that the epoch time is independent of the symbols, then the expected value of the product is the product of the expected values. You can't break it down into four individual terms, but you can do pairwise. The AK and AK plus M are grouped together, and then the term involving the delta is grouped together in a third term. So is that making sense? One term, second term. And that's from independence. That's fundamental in random variable theory, that you can't break a quadruple expected value out unless you can make some assumptions regarding independence. Uncorrelated would not work unless we wanted to model, well, it can work, I guess, but here it's easier to just say independent. Uncorrelated would be if the pieces involving delta are uncorrelated from the bits. Then that would allow the factoring that we've got here too. So maybe that's sufficient. I've always just said, assume the stronger assumption of independent. So we've got these terms in here. We've got a double sum still. We haven't eliminated that, but I've now interchanged. Well, no, I haven't interchanged. I brought in, I've expanded out the integral. This expected value requires that I average or integrate over the uniform distribution on delta, and that's all of that business right there. The expected value of the AK plus M and AK is written as the autocorrelation between the symbol sequences. So that's this sum in here is averaging the autocorrelation between the symbol sequence, just R sub m, and then we have the sum of the integrals that integrate from minus t over t to plus t. And I noticed when I was reading this earlier to myself, we don't really have a double integral, we just have a single integral, but I changed variables in the integral so that it's easier to manage what's going on inside of there. So I let u equal t minus kt minus delta, and then du is minus d delta. And then what's happening, and this is a slick trick that's used a lot in this type of formulation. For those changes, then these are the new integrands, and rather than the limits of integration running over delta, let's see, wait a minute, I'm going to get myself confused. Yeah, that's right, okay. So all I wanted to say is after the change of variables takes place, that integral is running over one bit long sequence. So if I So now what we're doing, this inner integral, the limits are such that we're running over a t-second interval. That's what these limits take you over, and it's stepping contiguously across the waveform, right? It's just going to step it over the entire waveform interval as k runs from minus infinity to plus infinity. So you can get rid of that inner sum. So the idea is now this inner sum combined with the little picture up above there means that I can just replace that by an integral that's running from minus to plus infinity. And the arguments stay the same. And then you can finally come down to saying, oh, what's that integral is what's called deterministic pulse autocorrelation function. So it's correlating the pulse shaping function P of t with itself, and that is going to provide the fundamental shape that gets Fourier transform when we go after the power spectrum. So this is the autocorrelation function of the random bit stream or symbol stream, depending upon what the RMs are. Then Fourier transform both sides, and we get this result, which is the Fourier transform of the autocorrelation functions, but we have to take into account this time shift. So this is the theorem. The time shift theorem becomes a frequency or phase shift factor in the Fourier transform theory. And this still looks kind of messy, but if you take the special case where the bits are uncorrelated, so bits are independent or uncorrelated from one another, then Rm is going to be 0 except when m is equal to 0. And then finally, you'd get just this result right here. It's just R0, whatever the bit amplitudes are, squared, times the Fourier transform of the pulse shape. So I've got a bunch of examples in the notes. I just want to quickly, well, you want to take a break and come back and continue on this with the numerical side of it?
Yeah, I think I could take a short break.
Yeah, okay, let's do it. The clock again means nothing. It's about 9:32, and that's my target time for the break. So, see you in about 10 minutes then. I'm going to stop the video and switch over to my Jupyter notebook. We're returning back from the break, and I noticed, did you get some coffee?
No.
Okay. I noticed there's a coffee stand over there. I mean, I don't drink coffee. They sell snacks, but I don't know how you eat snacks these days with a mask on, so. Okay, we're gonna look at this random pulse train. Just reflect back on the idea that, because we'll be using this a lot, we'll be extending this when we get into the modulation theory results. We're going to be assuming uncorrelated bits, but we could have correlated bits, so we're going to be using what I have in the blue box here, the Fourier transform of the fundamental pulse shape. So I have some examples in the notes which are based on what I used to do in MATLAB, and those MATLAB code bases are still up there, but what I have in the Jupyter domain over here, I'm using out of digitalcom.py. So at the top of this notebook, I'm importing from Scikit DSPcom, digitalcom as DC. You'll be using that package a lot as a springboard for doing a lot of different things. So digitalcom has got a lot of things inside of it. Stupid keyboard and fingers. Mutilate what I'm trying to do. And maybe this notebook was relaunched. Who knows? So I guess I better restart it. Oh, I didn't do the right thing. I needed to go to the top. Navigate down there using that. No, why didn't I not run? I thought I ran this cell. Start over again. I'm just using the table of contents, which is based on the markdown cells that you have to navigate more rapidly. Okay, so just to see what's inside of here, though, I was going to see if this will open up. It did. Took a while, though. I was impatient. So there's a lot of different things that we'll be using out of here, but right now I'm just going to be using NRZ bits, and there's even a couple of different forms of NRZ bits. There's one that lets you use random bits, and then one that lets you put in bits of your own choosing. So we're using NRZ bits, but NRZ bits 2 lets you put in, say, a PN code or your own type of bit stream that you'd like to use in creating the waveform. And then it creates a waveform. So if I go Shift-Tab inside of here, you'll see that the signature for this function is the number of bits you want it to generate. And in this form, it's just random bits, identically distributed. The number of samples per bit. So in the synthesis of a waveform, it's how many samples per bit. And the waveform types, in the notes I was using rectangle, raised cosine, and half sine. That was in MATLAB, but here I'm using wave shape or pulse shapes that are more important for shaped modulation of today. So we have rectangle, raised cosine, and square root raised cosine. And then you can control the shaping factor, the excess bandwidth factor, when you go with that mode. So we'll start off with the rectangle though. So the rectangle, I'm doing 10 samples per bit. There is the sequence, 100 bits. If you wanted to just zoom in on seeing 10 bits, that's what that would look like. So how can we estimate the power spectrum? Matplotlib has a power spectral density estimation routine built into this, and I'll be talking more about how this estimator works when we get into the next chapter with the first digital modulation chapter, but it's using a technique called Welch's method of average periodograms, which is a very popular non-parametric spectral estimation technique. I'm saying that like I've studied spectral estimation, and I have. I used to teach a class in it because it became a fascination and for some funded research, so I got interested in different types of spectral estimation. Sound believable? I mean, non-parametric based on the FFT is probably the most popular, but there are parametric types. In the detection and estimation theory, or the statistical signal processing class that I could teach next spring, there's a chapter in the book on spectral estimation techniques. And I'm mentioning that because I'm going to be meeting with Dr. Kelker, the department chair, to find out what I'm teaching next semester, because I didn't even know until Eva sent out an email that she said, here's the second round of schedule for our classes in the spring, and I looked at it. Because I'm on sabbatical, I get wiped off the schedule, and she doesn't put me back in, so I didn't see any classes that I'm going to teach for next semester, so I've got to get that figured out, what it is I'm going to do. Is there any interest in statistical signal processing? I'm throwing that out there because I'm going to be dealing it out. I'm planning on teaching real-time DSP, but that class, normally statistical signal processing would not be taught until next spring, but I'm planning on not being here next spring. I haven't officially decided.
One of the two.
Okay.
But I maybe need a better understanding of what real-time DSP is.
Okay.
Like.
Okay.
I'd be interested to take one of them.
Yeah, okay. Statistical signal processing always has about 3 people in it. It's ever since I've taught it. It's classical detection and estimation theory. You can read about it on the website, what it would be.
So is real-time DSP, is that Verilog or is it like
C on a microcontroller?
It's like Juice or some library like that, I imagine.
Well, the library I use is homemade C code with data structures and stuff. And then we also use the ARM CMSIS Cortex-M software interface standard -DSP library, which has been expanding quite a bit, but it has filters and other math functions built into that library. So it's
all software.
It's all software, but you're in the lab with the board, taking measurements, using instruments in the lab, and building and running and then controlling things. I have tools to allow you to control things on the fly. I talk to the board with a serial port, and then I have a little GUI so you can tweak parameters on the board code while it's running. So it's to learn about the concepts of real-time programming, making sure you're staying on time by monitoring, interrupt service times. We use sample-by-sample processing and DMA-based frames processing are the two types of mechanisms used in the class. Sample-by-sample is low latency, frames-based processing is greater latency depending upon your frame size.
Right.
But I emphasize the fact that both of those, the class, you get to see how that is. You might not meet your real-time requirement with sample-by-sample because it's too inefficient, so you go to frames-based processing and get a lot more efficiency at the expense of some latency.
It's like FFT-based filtering, right?
It could be that. I'm going to do that in the modern DSP class. I'm going to do that in C++. I'm going to have them explore that this time around. I'm changing the order of the material in that class because that's stuff I've been doing while I was on sabbatical, FFT-based processing. A lot of that. So I'll be discussing this with Dr. Kalker. The final decision won't be made, but if I propose a bunch of classes and then I get almost no enrollment, then I'll get into trouble anyway. So I have to decide what it is I want to do. At any rate, PSD is available it's actually in the matplotlib package. There is one in scipy.signal, but this is the one that I use most frequently is PSD. And so you get the typical parameters that I would use would be these first three. I would just put in the real or complex array. I would set the FFT length that it's going to use for the average periodograms, and then I would set in the sampling rate so that what gets plotted automatically gets returned in a plot. Now I also typically will see if this is in here. My PSD is something that I put in the SIGSYS package, and what it does is it just wraps a version of PSD where I can get access to the return, which at times to me is more important to get access to those arrays rather than let PSD autoplot. Sometimes the autoplots aren't what I care for, so that's also available. But for here I just up the number of bits up to 10,000, and so this is power spectral density associated with a rectangular pulse shape, which looks like a sinc function, a sine x over x in decibels. If I was to put inside of here raised cosine, then I'm going to get a very band-limited spectrum that's controlled by the excess bandwidth factor, which is alpha. So if I make alpha a little bit bigger, like 0.5, this will get a little bit broader. But in actuality, we're more interested in SRC.
Gaussian pulse.
We could use a Gaussian pulse, but that would have to be truncated. For digital communications, though, we're going to see that probably the most popular pulse shape is SRC, square root raised cosine, or RRC, root raised cosine, same thing. You've heard of that before, right? Root raised cosine or square root.
I've heard of it, but
Why? It's one of the fundamental topics of this class a little bit later.
we've used them as like model stimuli for simulations.
Okay.
Like we have our own little pulse shaping. We usually use Gaussian pulses.
Okay. Well, digital comms usually use square root raised cosine because you pulse shape at the transmitter and then you pulse shape to make a matched filter at the receiver. And so you have square root raised cosine and square root raised cosine, which together in a cascade is raised cosine. And we'll see how that forms the perfect matched filter for additive white Gaussian noise. So that's coming up. I'm not going to try to go into that right now, but that pair is really important. So that's kind of just showing you how that all works out in practice. And You see side lobes on here. Yes, they're present, and it has to do with how you're going to approximate things. So if you need to make, this is using plus and minus 6 tails on this square root raised cosine filter. Again, the details of that will be coming up in the next chapter. If we need more precision, like you might need to have better error vector magnitude, is what it would translate into, then you would need to make that bigger. So the default value is 6. If I put that up to 8, you'll see that the side lobes drop down faster or drop down smaller. There's whole discussions on how to best design, approximate a square root raised cosine filter. The filter has got an infinite impulse response, so you have to truncate it a certain amount. And we'll see the impacts of that as we cruise along. It looks like in here I also used my PSD so that I could customize the shape. And here I'm using, I don't even know, that was just using 100 bits. So it looks a lot noisier here with 100 bits. What did I do? I didn't show you what it looks like. I'll just do the RC on here. Then it has the wiggly stuff on it. Take that away. We'll be looking at eye pattern plots of this type of waveform too. If you're curious about how easy it is to do that with the tools, you would just, oops. That figures I always click the wrong thing and then I end up destroying something that I wanted to keep. Let's go back to this again so I could do that. Wanted to do that. So I could take a chunk of that waveform. It's already been matched filtered effectively, so it's raised cosine, and then I could take some of those bits. I'm probably increase this up to 1,000 to get kind of a full eye pattern plot. And then down here I could take X, and then in the eye plot I get to set the interval I want. The interval here is going to be the length of the window, so I'm going to make that 2 times 10, and then the offset here, I'll just set that to 0 and see what I get. There. Generally, I'd have to increase this because of the delay I've got, so I've got 6 times 10. That's how many samples I have of delay to get the filter charged up in the very beginning. Plus and minus 6 bits of tail on the pulse shaping filter. So if I do that, it should be clear. So we'll be working with that a lot. Okay. What? Because it's not perfectly open? Yeah. But it's you know why that is? It's because of the pulse shape. I could get it tighter if I would make that be 10.
Yeah, that's right.
And then I would rerun this again. Wait a minute, what did I do wrong? I don't know what happened there. Something strange happened though. Oh, I know what happened, I think. It could be 8 though. Honestly, don't know what's going on right there right now, but it's possible I messed something up. Yeah, there's something happening that I don't know exactly what I'm seeing. The waveform up here looks good, but I don't want to go troubleshooting it. I'm getting way ahead of myself anyway in that regard. So these are some other examples with some other pulse shapes. And another property of interest is what is the autocorrelation function associated with a random bit stream. So that example is also inside of here. where I would use an XCore function, and I would take my X, which is, gotta make sure I put this back to the rectangle again. And if I then look at the XCore on that, so I'm going to be correlating X with itself, so this XCore is forming the autocorrelation function using a single sample function, a time average autocorrelation function. And you see it approximates the theoretical value, which would be what happens when you correlate a rectangular pulse with itself, you get a triangle shape, and that's what we're seeing right there. It's got a little bit of wavering at its base because it's done with a random sequence. So this was an estimate of the. Which brings me to the need to jump over to one of the homework problems and just kind of tune you into that a bit. And these are the hints that I put up already, so you can study them in more detail, but you have a problem similar to what we did for the random bit stream, but now it's just going to be for a square wave of plus and minus amplitude A. And the idea here is you have to compute the time average and ensemble averages, and I'm just giving you a hint on how to do that. This is a different approach than, well, it's a similar approach to what you, with the it's not the same approach as the random bit stream. This is a waveform that has a random epoch now, so what is going to be its autocorrelation function? It's a periodic waveform, so the best way to set up this analysis for the time average is, or for the ensemble average, is to just consider the fact that you've got a waveform and a time-shifted waveform. For the time average definition, this picture applies as a hint. If you consider the, and that's what this integral down here is showing you, if you consider the ensemble average, after you change variables and apply the random time shift, it will work out in the same sense. You're going to have to explore that in working this problem. This is a little bit more involved than the typical problem in this assignment, but so I'm challenging you to take this on, and if you're looking at how the time average would work, and like I said, the ensemble average ends up being the same through changes of variable in the integration. So just considering the time average, we're multiplying one waveform times another, and for a given lag value of tau, non-zero, you have the product of the two waveforms, and then you can identify these four regions of integration. So that's what this hint is all about. These four cases have to do with how this integral is going to get evaluated. So case 1, case 2, case 3, and case 4. And this will help you figure out what the waveform is. But you know, because the waveform is periodic, its autocorrelation function is going to be periodic. So if this works, I did a little animation over here in Julia where I kind of put this together as a randomly phased sinusoid. So I don't know if this will work because of the video being on. Yeah. If I set this time back to 0, it's going to be at a peak, right? The autocorrelation of the waveform in itself is peaked. And then as the waveform lags, which is the red relative, it's going to reach a point when it's like that. So it's a quarter of a period lag, the red from the blue, and then the autocorrelation function is going to be 0. Does that make sense? If you look at the overlap of the two waveforms, you see one waveform pair is +1, -1, and then the next one is +1, +1, and then a +1, -1, and then a -1, -1, so that averages to 0. And then as this keeps moving, it's taking on that green dot is what the waveform autocorrelation is. And it completes one cycle and then it starts back up again. So you're going to come up with an expression in this problem that's going to be a triangle wave, but it's going to, the best way to analyze it on paper, this is not a simulation problem, this is an analysis problem, so I'm showing you this is a simulation that I'm doing here, but how you can write it out as a piecewise function, piecewise continuous function for one period, and then once you have the one period, then you'll have it for all cases. So one period would be, like starting at minus tau over 2, which I don't have that. That's not simulated on here because I didn't back up that far. I only backed up to a quarter. But if I was to do that, you'd be starting with one period. I would go minus t over 2 to 0 is one piecewise solution, and then the next one would be from 0 to t over 2. And that's kind of what you can do in this picture right here. Here I've got tau positive and then tau negative, and you're just overlapping it. This is kind of the best way of getting a handle on how to set up your regions of integration. So this is a little bit tedious, but it's very doable. You just get 4 little integral pieces, and then they come together. Sound okay? Draw sketches, draw pictures to visualize what's going on. And we'll talk on Slack if you've got questions on it. The rest of the problems aren't too bad. We already talked about the simulation part. But I guess I can come back and rediscuss that. The first two are in random variables. I think those are pretty good. This third one is a simple random process, getting the PDF. I've used this problem before, so disregard that. That showed up in here. I shouldn't say that, but I think I can talk about it if you want me to. It's just getting a simple PDF. But I'll revisit any of these discussions. I mean, you have your choice actually in the simulation. You can get your matrix using the approach that I've hinted at over in here. That's in this notebook, and this notebook is on the website. I've actually got information on the square wave, so you can create a square wave simulation, kind of like I did in Julia. This one just isn't animated, but it is put together, so you can simulate it, play with it, understand the math part of it. Remember, I said this before, sometimes I have to do a simulation to get inspired to understand the math. That's backwards for maybe a lot of people, but that tends to be the way I am about things. I need to get my feet on the ground. In terms of the simulation, though, this builds you up how to build up this big rectangular matrix that has all of these waveforms in it that are the sample functions that you could get to control how many sample functions you create. And this just gives you hints on how to do that with the product of matrices, where one matrix has the time-varying function in it, and then the second one applies the random phase part to it. So that's a clues as to how to build up an ensemble like this. Anybody thought about it since last week? Or do you just want to sit back and ask me questions later? If you're not ready to ask questions, I'm just going to go back to the lecture.
Yeah, I'm not ready.
Okay.
I haven't thought about it too much.
We have Slack though, right?
Yeah.
Okay.
It's due
If it's due next Monday. If things go really south, I mean as in bad for you, talk to me on Slack and I'll contemplate an extension. And I mean this for you, Robert, who's watching the videos only. Keep me informed. I mean, this holds for all three of you, and my other DSP class in particular, I gave them an extension because I knew there were issues, and then people still didn't spend time, and I reminded them on Slack. I messaged them, I said, I didn't get your paper when it was due, and now I'm starting to deduct points. For this class being so small, I don't have a need to do that. I would rather just say, hey, if you need more time, let me know. If it's extenuating circumstances, like this is happening right now and I can't get the time that I want to know about it, but I do want to keep things pushing along, because if we just stagnate, we won't get anywhere. So, but let me know on Slack, and then we can do the channel thing. If you talk on the CompTube channel, then you can just go at channel or something like that. You know, everybody know about the adding thing, or the at command over here in Slack. If it's going to wake up here, it might need to be restarted. It looks like it's still here. This team, right, this is one of my design teams, so she talked to me and use ampersand to key me, and I've been keying them by making sure everybody gets an alert by doing at channel. For you guys, it's just 4 of us that are in this channel. I don't think I've done that here, though. I haven't done any channel. Oh, I guess I did. So, here. Just blew up. I just lost my drawboard. It just crashed on me again. I think they may have made this too fancy, and I'm beginning to wish I would have stayed with the old version.
What software?
It's called Drawboard. See how slow it is to getting going? It's letting me read this tip, but it's saying it's loading documents. I'm ready for the show to begin. This is an Australian software company that developed this, I think, mostly for architects, so they could do all of their work on drawings without ever using paper. Wow, this is really slow. I wonder if it's because I'm running the video right now. Okay, will it let me do this? This is where it crashed before. Okay, so our next topic up, well, I didn't mention this, but this is the definition of the cross power spectral density. It's the Fourier transform, the cross correlation. Where does it get exciting? This gets exciting in system identification. That's where I bumped into it. In control systems, people might use this. We haven't seen what a white process is formally, but if you could drive a system with white noise, and then you could use the cross spectrum as a means of getting at the frequency response of the system. Has anybody had controls where they've seen the idea of the cross spectrum as a way of getting at that? I'll try to point that out when you get through white noise. It can be a system identification means if you're driving a system with white noise.
I guess, why would you do that instead of just driving an impulse?
Or a sinusoid sweep.
Yeah.
Because the stimulus is more easily applied, I think. You'd have to ask Dr. Trimboli that in your modern controls class.
Mm-hmm.
Sometimes, though, systems can be characterized on the fly, so that's where that could also be useful. that one stimulus is already inherent in the system. Okay, random processes with systems. So we've only been focusing on X. Now we're going to pass X through a linear time invariant system like a filter, a linear filter. So we care about now getting over to Y. So very simply, to get the mean, you just want to take the expected value of X convolved with H of t, because that's an LTI system. We know that the output is the convolution of the input with the impulse response of the system. And because the system is not random, we can factor that convolution out, and then we just have the expected value of X, which is going to be m of X times the integral of the impulse response, which from the frequency domain would just be the DC gain of the system, or H0. So this is not all that exciting. Just say the output mean is the input mean times whatever the DC gain is of the system. This is like, I know that, right? If your system was capacitively coupled or didn't pass DC, then the DC gain is going to be 0. The excitement is in getting the autocorrelation function at the output. So the autocorrelation function at the output would be the expected value of y of t plus tau times y of t. But then in order to actually do that, you've got to blow things up. So you have to have one convolution and a second convolution when you start expanding it. And this gets to be tedious. If you jump inside of this, though, and write out the double integral that you're going to have here, and then take the expected value of that double integral, you can simplify things down, and you'll have x of t plus tau times x of t. That's the only random part in here, so that brings us Rx of tau. But then because there's two convolutions hanging out inside of there, and one involves h of t plus tau and the other one involves h of t, you end up with h of tau, and then you end up with h of minus tau. And that's due to the way convolution and correlation are related. Convolution would be the h of tau, but then if you're doing it with a correlation in there, h of t plus tau, that makes it look like the negative of a convolution. Because a convolution, remember, you're taking one thing times the other flipped, so one's going backwards. When you're doing a correlation, you're taking the waveform times itself, and that could be written as a convolution where you're flipping twice, and that's where the minus sign would appear. I don't have that detailed out in here. It's something that I spend more time on, I guess, when I teach statistical signal processing, just to see how that comes out. I'm just trying to give you the high-level view of it, though. It's the input autocorrelation, and then it's h of tau and h of minus tau. And so this is like system correlation. So to write it as a convolution, we have to write it with the minus tau in there. That's another way of thinking of it. You're getting the autocorrelation of the system's impulse response. And to write it in terms of convolution, we put the minus sign in there so that it flips it twice. Does that sound right? You know, it has to be, convolution is one waveform's flipped from the other. Correlation is the right. So if you are doing a correlation between two waveforms, it can be written as a convolution of one that's flipped, one with a negative. So that's what the final form. There's the RH of tau is the system correlation. So that's this guy right here. Our h of tau. We actually saw that in what we were doing that simulation where we had the pulse shapes, square root raised cosine and rectangle. If the data stream was an impulse train rather than an actual pulse shape, then we're applying the autocorrelation function of the random impulse train with a convolution with this triangle shape, which would be the two rectangles convolved, and then that gave the sinc function or sinc squared spectrum. I didn't go that route though, but we could do it that way. In actuality, that's tends to be the way most digital modulators work. They will take the symbols at one sample per bit, so they'll either be, say, a +1 or a -1 bit, and then they will upsample that by some factor, say 10, and then we'll have 9 zeros stuffed at the end of each of the bits, and then we'll send that through an FIR filter, which is the pulse shaping filter. So that's kind of a way that you would do that in FPGA or in software by upsampling and then shaping. I'm sure that's stuff that it's done in your stuff too.
Yep.
Where you upsample. Cross correlation is something that happens along the way. So it's another way of visualizing what the autocorrelation function is. If you were getting the cross correlation between the input and the output, you would have Rx of tau times h of minus tau. So this is where the system identification part comes in. We now know that the cross correlation is the stepping stone. That's if I was to take all of that and bring it down here, this could have been Rx of tau and then pass that through again. This thing won't let me do it. So that's a way that some books draw out a block diagram to show what autocorrelation at the output of a system looks like. It looks like it can be broken out to look like the cross correlation between the output and the input, and then the final convolution of the system's impulse response, which is what this result is. Well, this is the cross correlation, and then that's what's up in there. Now, sort of the punchline on this stuff is if we're going to go to the power spectral density domain from the autocorrelation at the output, this is a very fundamental result. It says Fourier transforming both sides and operating with a convolution theorem. So this uses for the Fourier transform. So now we have the product, and we know that the Fourier transform of h of minus tau is h conjugate of f. That's another theorem in Fourier transform pairs, in Fourier transform theory. So conveniently, because of the way that those two things stack up, we have h times h conjugate, which is h magnitude squared of f. And this is fundamental result. It says if a filter is applied to a random waveform and we want to know what the power spectral density is at the output, we just multiply it, the input, by the magnitude squared of the frequency response for modeling purposes. Very, very useful result. From the cross spectrum, though, because of the way the cross spectrum works, if you're cross correlating x with y, then the cross spectrum x with y looks like this top line, or if it's the bottom line, if you're going to do y first, then you get this more usable result, which says that you can identify the system from the cross correlation. If that was white noise, then the cross spectrum output with input would be a constant. That's what white noise's spectrum would be, a constant times the frequency response. So that's the system identification thing I was mentioning earlier. I guess white noise the definition comes up here shortly. The way it's going to come up here shortly. Okay, how about signal plus uncorrelated noise? So we have signal plus noise. We're going to assume that the cross spectrum between the signal and the noise is 0, and the mean of the noise is 0. So then the power spectrum is just going to be the sum of the two power spectra, the input and the cross spectrum. Remember, when we were looking at the autocorrelation of the sum of two processes that were uncorrelated, then the cross terms dropped away as long as one had 0 mean, and we just get the sum. And this is the common signal processing scenario. This gets extended in wireless by saying we have many received signals that will impinge upon our receiver, then we have additive noise, we have all of that superimposing as a result of the uncorrelated assumption. All the other users and interfering terms or intermodulation terms, all kinds of things can happen. Example I went through here was just saying we had an RC low-pass filter. Know what its frequency response is. Magnitude of the frequency response is the 1 over 1 plus quantity 2 pi FRC squared. So that would be a way of seeing what the shaping factor would be on the noise spectrum SW and on the signal SF. This kind of thing will be done in the modulation chapter coming up next. What about Gaussian normal processes? We know Gaussian random variables seem to be immutable if we do linear operations on them. So if we have, when I say immutable, I mean they don't change, they stay Gaussian, even though you beat them up with a linear operator. And homework problem number 2 is exactly that. Homework problem number 2, you're taking a function, I don't want to risk killing this thing by changing to my hints page, but you're taking a random variable x, I think it's z is equal to x plus 3y or something like that, and you know x and y are correlated Gaussian. When you form the new random variable z, it's going to be Gaussian also, because if it's a linear combination of two Gaussians. Linear, uncorrelated or correlated, it's still going to be Gaussian. So in this case, suppose we have jointly Gaussian process. This is just talking about random process X. We're sampling it at 2 different sample times, T1 and T2, so we denote those random variables as X1 and X2. The correlation coefficient rho is related to the autocorrelation function minus the squared mean, and then normalized by sigma x squared. Important properties, though, when we have Gaussian processes is that all we need to know is the mean and autocorrelation function to characterize the process. So we pass the process through a linear time invariant system. It gives us another Gaussian process. And if a Gaussian process is wide sense stationary, it's also strict sense stationary. That's a very important assumption for making sure that we can utilize the full capabilities of the Gaussian assumption. And then ergodicity of a wide sense stationary 0 mean Gaussian process just says that the integral of the magnitude of the autocorrelation function is less than infinity. So that allows us to make this ergodic property stuff happen for Gaussian processes, which would be noise. And uncorrelatedness and independence are equivalent, and that follows from Gaussian random variables that are uncorrelated. So the next kind of significance of Gaussian processes is if you filter them, good things happen. If you filter a Gaussian process, it stays Gaussian if it's a linear filter. And really you can kind of get a handle on that from the convolution sum, namely that it's going to be a linear operation, so you're going to be just forming sums of Gaussian random variables when you go through this approximation of the convolution integral as a convolution sum, and whenever you add Gaussians together, you get another Gaussian. Now we'll talk about white processes. The formal definition of it, white, comes from the idea that white light includes all colors, and all colors means it's all spectral components. So it's not possible to really have it true as a constant n naught over 2 for all frequencies, but in the frequency of interest, it is true. I think I have, if I go down here, thermal noise off of a resistor, the spectrum looks something like this. If we're, say, 300 degrees Kelvin, which would be room temperature, the model is up to at least 10 to the 12th hertz. It's pretty flat at room temperature, and that value is minus 174 dBm per hertz, or minus 204 dBW per hertz for thermal noise. So it's constant. I mean, the autocorrelation function is a delta function, so the spectrum is constant. And that's just the Fourier transform of a delta function. And that assumes a Fourier transform in the limit, but that's acceptable from an engineering standpoint. So constant or flat spectrum. And then the rest of the details are getting the physics involved to get the levels. So white noise in the time domain is uncorrelated from sample to sample, and that's the property that we utilize in modeling systems, and that's why if, say, a measurement of a voltmeter makes on a somewhat noisy probing of a DC circuit, it will be impacted by some measurement noise in the front end of the voltmeter, and maybe it's riding on the signal, but the measurement can be averaged very effectively because of the uncorrelatedness of the noise. In other words, by sampling, combining values from adjacent samples, you've got uncorrelated noise, so that gives you the full power of the averaging. Correlated measurements don't really help that much because you're not getting any new information. You're getting the same noise value, let's say. It's not changing that much. Okay, some more discussion about physics and random motion of charge carriers. Central limit theorem tends towards Gaussian. And this is the spectrum, which has Planck's constant in there to show the frequency dependency of the white noise model, and that's how this plot gets generated. So I think we're safe with 5G. What's the highest frequency of 5G? Is it 60 gigahertz? You're studying that with Dr. Simiari. It's around 60 or so, or what?
Yeah, it's around 60.
So we're still under 100 gigahertz, so our white noise model still works, I guess is the point. Unless you're going to go down to a much colder temperature. We're just about out of time. I'm going to just introduce this and then we'll come back at this next time. Noise equivalent bandwidth is an important concept in digital comms and in RF communications theory in general. So it's good to get it defined here. If we have a filter that's applying some shape, and I think I have a picture, yeah. So I have a picture, the blue line is, say, a low-pass filter, exaggerated amount of ripple, but it then tapers off into the stop band and goes down to zero pass band or zero gain. So the rectangular filter idea is what the noise equivalent bandwidth is. It's saying what filter that's ideal and it's has a rectangular frequency response equates to the true filter. So it's just a useful concept to talk about noise equivalent bandwidth. When I worked in industry, we had certain test filters that we would use in some of our measurements, and they were maybe Butterworth or Chebyshev or something, but we would have the noise equivalent bandwidth written on the filter so that you would know how to calibrate noise power from a spectral density measurement. Another way of getting at that was we would have a power meter in the lab and just make the total power measurement, because that would give us what this integral would be when you integrate the power spectrum from minus to plus infinity, assuming that we're driving it with a white noise source, and then the single-sided is just because of symmetry, but a power meter can do that. But nowadays, that combination is frequently on the spectrum analyzer anyway, so it's able to get that calibration done for you. Noise equivalent bandwidth measurements to get noise power in a measurement. But in my day, I didn't have a spectrum analyzer that had that capability inside of it, so we would take measurements, assuming we had a filter that we calibrated its noise equivalent bandwidth for already. Turns out for a low-pass filter, the noise equivalent bandwidth approaches the 3D bandwidth as the filter order goes to infinity. So this is just an equation that shows you what that integral turns into for arbitrary order. It's just a kind of a curiosity thing. It's not something that you use that often, but it is something to make note of. As the order goes up in a say Butterworth filter, the 3 dB bandwidth is the noise equivalent bandwidth. That's just kind of comforting, right? Okay, we'll pick this up next time. Narrowband noise, very important for modeling in RF systems. How we can work that complex baseband, and this is where the complex signal processing comes in, which is what most DSP comm systems use. But how we start in the RF domain, we assume we have an IF bandwidth or RF bandwidth, and then we can model things in terms of in-phase and quadrature noise processes. And this will become just standard operating procedure in the next chapter. If you want to live at baseband, we don't need this, but I don't want to live at baseband because I do want to modulate carriers and transmit signals. Our lives depend upon that. My watch is talking to my phone, and my phone is talking to the cell tower, and, well, you know the rest of the story. We rely on that, so. Okay, we'll pack up and we'll start on this for next time. So if I can get this thing to stop.